Hello, this is chapter 5 of the Top Hat textbook. In this chapter, we're going to be starting to think about alkanes and other molecules in a more three-dimensional shape. How about that? So the first one we're going to talk about is just the simplest form, and what are called Newman projections, which allow you to see how the atoms coming off of two different carbon atoms are interacting. And then we'll talk about cyclic structures and how we can use Newman projections to understand how the conformations of the different cyclic structures. So the first thing to do is what are called conformers. So conformations are just the temporary shapes that these molecules can undergo. And don't forget that if you have just a sigma bond here, just a single bond, you can get free rotation around the bond. And so there's a couple of different ways that we can show that. The first one is, and the one that we're going to be talking about in this chapter is Newman projections. But you can also use a sawhorse formula. And don't forget, when we look at this, a normal sort of line means it's in the plane. A wedge is coming out at you, so this one and this one are coming out at you, and then the dash, those are going away from you. And so with the Newman projection, what's happening is we are looking, so if you look at the simplest one, in this case it would be ethane, what we're going to do is we're going to rotate it so that we can look directly down the carbon-carbon bond. And so you have the carbon in the front, and you can see the three hydrogens hanging off of it, and the carbon in the back it's going to be obscured by the carbon in the front, but you can still see the hydrogens sticking off of it. And so if you take your model kit, right, so I'm going to try to do this here, and so you've got the carbons, right? So like this, you got ethane. I've got some balls to help you visualize it, and so if we rotate this around, what's happening is, right, so you can see it right directly down that bond. So this carbon you can see, but the carbon behind you can't because it's obscured by it. But you can see the hydrogens that are coming off of the other, the back carbon. Okay. Now, a couple things of terminology. First one is what's called the dihedral angle, and so this one is just if you've got a group in the front on the front carbon, a group on the back carbon, what's the angle between this? And so for this one, if we're talking about this red one here and this blue one here, that would be 180 degrees. So if we're talking about this red one and this blue one here, it's going to be 60 degrees. So that's all we're talking about. Not between on the same carbon. That's always going to be the same. But we're talking about the one in the front, one in the back. Okay. So this is the form. So one thing I forgot to mention: if all the dihedral angles are 60 degrees, okay, so they're like this, we call this a staggered configuration. So in this case, the hydrogens are staggered between each other, right? So we're going to be staggering this. All the dihedral angles in this one are going to be, let's see, I'll show you this it's a little better, but it's 60 degrees. So that one's a staggered configuration. It can also do an eclipsed, and in this case, like this, right? So here the dihedral angle between the reds and the blues, as well as these, are going to be 0. But just like these, this carbon here is obscuring this one would be obscuring this one would be obscuring that. So typically it's drawn in this way. So if you look directly down, you wouldn't be able to see anything in the back. But typically when it's drawn out, it's drawn like this. So it's sort of cocked to the side, so that you can see what's hanging off the back. And again, it's assumed that you could that the carbon is in the back. So this is an eclipsed conformation. Staggered conformation has all the dihedral angles at 60. So if you look at this, with that. So we're going to be mostly talking about steric repulsions, and here they're the maximum distance, social distance that they could get on here. With that, so you've got this. So this is a staggered form, right? So this would be 60, right? And then this one, there would be a 0 dihedral angle on that one. So just like when people who don't know each other, they get onto an elevator, what happens? They move off to the corners to give everybody space, right? So at the same thing here, and if when they're in the staggered form, right, they give the maximum amount of sort of personal space for each atom. When you get into eclipsing, what happens is you're starting to see these groups, the one in the front and the one in the back, are starting to feel each other. They're starting to get a little bit too close, and so they start to repulse a little bit. And this is what are called steric repulsions. It's just basically two atoms that are starting to get near each other, and so if you try to push them farther together, or closer together, I should say, then it's going to cost you energy. And so in this case, you're going to get not only the ones here, here, and here. So with that, so you're going to have 3 eclipsing hydrogens. And so it's going to cost you some energy, but as soon as you rotate one of those carbons around, then you get back into the steric position. So in this case, what's happening is it's keeping the front, it looks like it's keeping the front one centered, or sort of fixed, I should say, and then it's just rotating this to eclipse and then back to staggered. So if you just so for here, there's no eclipsing interaction, so it's at the lowest energy. Now, if you were to look at butane, okay, it works the exact same way, but instead what we're doing is essentially, you can think of the easiest way to think about this is to say, okay, well, instead of hydrogen, we have the methyl sort of think about that. But so in this case, we're gonna rotate the front one, and so if in this here, if the two large groups, the one on the front and the one in the back, if they are 180 degrees from each other, that's what's called the anti-conformation. So this is the lowest energy state for the molecule. Okay, because the biggest things are as far apart as possible. Okay? But as we rotate this this one around, right, this comes here. Now you've got eclipsing interactions here, here, and here. And with that, and so as we rotate around, right, now we're starting to get into this right here. So if you've got this situation, so you say, oh, they're staggered, so they shouldn't be. Well, yes and no. They are. Yes, they are staggered. But remember how the hydrogens are sticking out from each other? So they are significantly bigger than a hydrogen. So when you have two large, it's basically two non-hydrogens, 60 degrees from each other, they're going to start interacting. And so this is what's called a gauche interaction. With that, so when you have a dihedral angle of 60, they're staggered, but they're right next to each other, they're not hydrogens, then you're going to feel it. So there's no gauche interactions here or here because the hydrogen's just too small. But once you start getting beyond hydrogen, you will. With that, and so you've got this one, you've got maximum, let's see so you can see it. You've got maximum eclipsing going on here because you have the two biggest groups right on top of each other. And so this is going to cost you a lot of energy. And again, you're going to have a gauche interaction here. And then you come back to the eclipsing, and then you rotate around, you go back onto here. Okay? And so if all you have to do, and if you were trying to calculate this, all you have to do is get a table like this and just add things up. Okay, and so with this one here, right, we've got, so this is the indication of an eclipsing interaction. So for here, you've got a hydrogen and methyl eclipsing, so this is worth 6. Again, that's what this is, and then 2 hydrogens eclipsing, that's worth 4. And so 4, 6, 6, right? So this conformation is worth 16 kilojoules per mole over your anti-configuration. And here, right, so it doesn't go, when it rotates around, yeah, it goes staggered, but it doesn't go quite down to 0 because you've got this single gauche interaction, right? That's worth the 3.8. And then you come back here, oh, now we've got methyl-methyl eclipsing, right? So that's worth 11. This one hydrogen, this is worth 4, and then this one is worth 4. So with that, so 11, 4, 4, so 19. So it's even worse than a regular the eclipsing interaction. Again, you're going to have, with this one here, you're going to have this gauche interaction, which is worth 3.8. And then here, you've got these guys here, so it's 6, 6, and 4. And then back to your anti. And so you could keep doing this as it's rotating around. So this is a nice little exercise to get you in here to start recognizing the what interactions are here and there. So, yeah. So they talk about torsional strains. It doesn't really matter. So as a torsional strain is just how it's kind of trying to twist itself to be able to get it out of interacting. So it knows how it's twisting a little bit. So it's not quite there. But you can really just think about it as steric strain, which is just basically two things getting into each other's personal space, and so you have to put some energy if you're gonna force that. Okay, so for cycloalkanes, okay, so for this one we're going to talk about sort of steric and what's called ring strain. Okay, so for that, so ring strain is how much you're putting a bond, sort of a normal, what should be 109.5 tetrahedral, out of that angle, something like that. And so it's sort of like if you were to bend your shoulder backwards, right? So with that, so for here, for the cyclopropane, right? It's actually, if these were flat, this bond angle would need to be 60. It wants to be 109.5, and so it's bending out by 49 degrees. You mean this would hurt your shoulder, and it costs a lot of energy to be able to do that. And so there's a lot of ring strain to be able to make a cyclopropane. With a cyclobutane, it's not quite so bad, right? So it's this internal angle is 90, so you're only talking about out of ideal by 19 degrees. With cyclopentane, right, we're at 108, right? So with that, so this is, if this was flat, right, we'd only be off by 1 degree. So yeah, that's fine. So with that, so and actually, if you went to cyclohexane, you'd actually be, it would go back up, right? So that, because the bond angle would be 120. So now you're getting a little bit further the other way at 11 degrees. Okay, so there was a big debate about whether these things were flat or not. So for that, and so if you just calculated this, you would expect the cyclopentane to be the most stable, and then it starts to become less stable as you start adding additional carbons in the ring. So that, but once they finally had these in the lab and could test them, it turns out that the cyclohexane is in fact the most stable configuration, is the most stable form, which means that it's not flat. That the lab data would say, look, something's up with that. So, and it turns out that you have to deal with these with all these types of strain. So you get angle strain. This is how far out of so that's what's going on here. So how far out of ideal is that carbon bond, right? So it really wants to, that carbon bond wants to be tetrahedral. It wants to be 109.5. Here it's 60. Here it's 90. Here it's 108. So that's really how far away is it from the ideal. Torsional strain is if you have eclipsing interactions, it can twist a little bit to relieve that. Okay, so it's like if you are leaning against a wall and you've walked a long way, your feet hurt. So if you're leaning against the wall, what do? You put your foot up, right? So you can twist your hip a little bit in order to be able to relieve some pressure. That's what's going on here. Okay. So for that, and then steric strain, that's just the repulsive interaction. You know, when two atoms are getting too close to each other, they repulse. Something like that. So we have to deal with this. We won't talk much about this. So for that, we're just going to talk about overall strain. Okay, so for cyclopropane, as it turns out that, you know, the reason why we talked about Newman projections before is because we can use this to explain what's going on with the cycloalkanes. So with the cyclopropane, if you come in here and look at as a Newman projection, what you have to do is you have to have, so if this is, say, atom 1, 2, and 3, so atom 1, 2, and then 3 is behind, what would happen is, notice how you've got these really nice eclipsing hydrogens here. And so not only do you have all that ring strain, okay, but you have these eclipsing interactions. And so all of that is adding up to something that is very unstable. So when you get to cyclobutane, it's not quite so bad. Okay, so if you're going to go, say, 1, 2, 3, 4, right? So for that, so 1 is behind, 2 is here. Oh, actually, let me do this. 1, 2 is behind, 3, 4. So what's, it can, you put a little torque, it can twist itself a little bit to have these things not be quite so eclipsing. Okay, so there is a little bit of distance between these eclipsing hydrogens. Okay, so it can kind of, shift this out so it's not quite so bad. So it can relieve a little bit of that, the eclipsing strain. Okay, when you get to cyclopentane, now you're almost, so if you look here, right, so you're talking about, 1, 2, 3, 4, 5, right, so with that, you're not quite staggered, okay, but you're pretty darn close. Because if you can kind of pucker it, you sort of pucker the ring a little bit, then you can get these things not quite as, almost to a staggered configuration. So there's not much strain from that. Okay, but once you get to cyclohexane, notice how these things are all, if you look just like this, all of these are perfectly eclipsed. If it gets into what's called a chair structure. And then for here, what's happening is it looks like a chair. And so I can hopefully I can sort of get this in the camera. So what's happening is, right, you've got your, maybe you can see it like this. Well, anyway, you've got your head here, you got your feet here, you've got your butt right there. Stuff like that, your body and that kind of stuff right there. And so it adopts, if it puts one of the carbons up and the opposite one down, then you can then you adopt this configuration, and notice how all of these hydrogens are perfectly staggered. Okay, and so this accounts for the fact that, and there's no ring strain, and there's no angle strain because the bonds are 111 with that, and so which is pretty darn close to 109. With that, so there's really very little strain going on with this in this configuration. Okay. Now, with this puckering, stuff like that, so of the cyclopentane, it actually, what happens is you get this, you can get one carbon that kind of comes out of the plane, and then it shifts around as it goes around. But this has been described as an envelope structure, and it's by doing this, you can relieve this, you can put these hydrogens in a much more, a nearly staggered conformation. So that's why it does it. If you were to, so with the cyclobutane, right, you can get at least a little bit of twisting, so that's to get these things, not quite eclipsed, so that so slightly out of eclipsing, so that helps significantly. But in the with the cyclopentane, there's nothing you can do. There's just not enough room to be able to move around much, something like that. So Okay, so remember with carbon-carbon bonds, you can get rotations. When they're in a chair structure like this, when they're in a cyclic structure, okay, when they're in the ring, they're still going to wiggle around, but they can't go all the way around. So they can go back and forth. And so if you've got something like this, right, you can wiggle it. This is where this chapter and the next chapter are good for where to have a model kit. So we can wiggle it back and forth like this, but it can't go all the way. It can't go all the way in. So like that. So you can wiggle around, and all these carbons can do this. Okay. So that's what's called a pseudo-rotation. Okay. Now, first things, we need to get some terminology going here. Okay. So every carbon, okay. So if we're just talking about cyclohexane, okay, every carbon's going to have 2 hydrogens on there, and each carbon is going to have each one of those hydrogens can be designated as either axial or equatorial. And we'll talk about that. That means equatorial. We can also designate them as up or down. You can have axial up, you can have axial down. You can have equatorial up, you can have equatorial down. These are 2 independent things. Okay. So up and down is the easier one to figure out, right? So for here, the this black E is higher than this red A, and so we designate this to be up and this one to be down. Okay, but in the carbon next to it, right, the A is above the E, so that means we designate that to be up and that one to be down. Okay, and we can go back and forth on here. So this would be, so if we look at this one, right, so this one compared to that one, right, this one is higher than that, so that's up, down. For here, this is down, that's up. Here, this is up, that's down, and then this would be up, and that's down, right? So this compared to that, this compared to that, so that. Now, the axial and the equatorial, those are the ones that are a little bit more difficult to determine, although it's not that hard. Okay? So what we do is we say, okay, so if you look at if you're comparing these two, if it's going straight up or straight down, okay, just like the axis of the Earth, right? It's either North Pole, South Pole, right? It's going up and down, stuff like that. So it's the axial either has to go straight down or straight up. If it's going off to the side like this, like it's pointing towards the equator, okay, we call that equatorial. So for that, and so it's not quite exactly straight over. It's sort of because of the tetrahedral shape, it needs to go. It's slightly up or slightly down, but it's basically pointing off to the side. Okay, and so if you have a carbon and you want to figure out which way the axial goes, what you do is you sort of look at if you look at here, right? Notice how the carbon-carbon bonds are pointed essentially down. So that means the axial has to be going down. If the axial is going straight down, that means the equatorial is going up. But for here, notice how the carbon-carbon bonds are basically pointed up. So that means the axial has to be pointed straight up, which means the equatorial, which is off the side, is going to be down. Same thing here, right? So carbon-carbon bonds, right, pointed down. So that means the axial is down. So equatorial is in the opposition. Now, this is off to the side, but it gets a little congested in here. So for this carbon and this carbon, you just kind of do your best. But for here, right, you have the carbon-carbon bonds are basically pointing up, so that means the axial is up, equatorial is down. Okay? So you can do that for all of it. So you can designate, right? So equatorial up, axial down. For here, this is axial. It's higher than this one, so down, right? Here, the axial has to be pointed straight down because that's where the carbon-carbon bonds are pointed. So it's straight down, right? That means this is axial, means that one's equatorial. So, and you go all the way around. Okay? Now, as if this thing couldn't get more complicated, okay, you can notice how, remember when we talked about those pseudo-rotations, you can get these things can wiggle around, okay, and so what you can do is, right, so if we put, what can happen is these things can do what's called a chair flip. And so I'm going to number these 1, 2, 3, 4, 5, 6. Right. And so 1, 2, 3, 4, 5, 6. Okay, so you can say you've got your little stick guy here, right? So his head's up here. Right? He's happy. Right? So with that, and so his head is up here, right? So with that, so his body's in here, and then his feet are down here. Right? He's lounging on the he's lounging on the beach. Uh-oh, something happens and you do a chair flip. What's happening now is that now he's not real happy, because now his head is down here and his feet are pointed up. Okay, so with that, so that's what happens with the chair flip. If you look at it in the molecule, right, so what's happening is this has come down and that's come up. Okay, so the and so this is what happens, and so we have to account for this with here. But one of the things to notice, okay, we'll do this here. Okay. So if we look here, we've got the green one, and we've got the white one. So the carbon-carbon bonds for this one are pointed down. Okay, so that means the axial is going straight down. Okay, so this is the axial down. And then this one right here, because it's pointing up to the side, it's equatorial, but it's above this green one. So this is the up and that's the down. So equatorial up, axial down. After we do the chair flip, that flips up here, the other side flips down. Notice what happens. Now the carbon-carbon bonds are pointed up. So that means this white one is what used to be the equatorial is now the axial. And the green one is now equatorial. That happens to all of these. During a chair flip, all the atoms that were axial are now equatorial. All the atoms that were equatorial are now axial. So it flips. Okay. But so when right? So when you get the chair flip, right? So this is right, so here, right? The carbon-carbon bonds are pointed down. So that's down, that's up. So this is axial. And this one's equatorial. After the chair flip, now the carbon-carbon bonds are pointed up. Now this one, right, so that means this is the axial now, and this is the equatorial. But notice what did not change. The bromine is still above the chlorine. So this is still up, it's just axial now. This is down, but now it's equatorial. Okay, so the ups don't change. The downs don't change. It's just the equatorial and the axial. That's the only thing that changes. Okay. Now you can get partial flips, so only one side has been flipped up. When that happens, you get what are called flagpole interactions. And so what can happen is let's see if I can show you this in nice way. So if you get what's called a boat structure, because it looks like a little paper boat, what can happen is when it's in the structure, you can get these two guys knocking heads with that. And so if there's ever a question about which one of these configurations or conformations is most stable, you can automatically get rid of any of the boat structures, because that is never going to be the most stable. I mean, basically, I'm sure there's some rare exceptions, but for the most part, you're going to end up having you're going to have the chair flip being the chair conformation be the most stable. Okay, and so if you look at the, just like we did with the Newman prediction, we look at all the interactions, right? So if you have a chair, if you have that as it's turning into the boat structure, it goes flat and then comes up, and then as this one comes down, it sort of twists down, goes down, and then comes back down. Again, you don't need to know this, other than chair is a much lower energy than a boat. Okay. Now, the easiest way to do this that I've found to do to draw a chair structure is to start with these middle carbons, okay, and interconnect them with a line, okay, and then you put one carbon up, one carbon down, and then just connect the dots. Voila, you got yourself a chair structure. Now, if you, so I'm gonna label these 1, 2, 3, 4, 5, 6. If you want to do a chair flip, okay, what you would do is then still do the ones in the middle. Now all you do is this one, instead of being down, you put this up, and 4, instead of being up, it's down. Voila, you've done a chair flip. Okay, and so 1, 2, 3, 4, 5, 6. Okay, that's the easiest way I found to do it. You can get all fancy if you want to, but when you're starting out, that's how I usually teach it. Okay. Now, if you have what are called monosubstitutes, so what we've done is we've substituted the hydrogen for something else. It doesn't really matter what, something like that. And so what can happen is, in this case, we put it as a methyl. Okay, so we got a methyl here, and then after we chair flip, okay, what's axial would become equatorial. Okay, so as it turns out that what you want to do, so these are not equivalent in energy. Okay, what's happening is when you've got a large group in an axial position, what's going to happen is you're going to have these, you're going to be interacting with the other axial hydrogens. So this methyl group is interacting with this and this, right? So it's getting really close. They're getting really close to each other. So this is actually not going to be a particularly stable conformation. So what it does is it's going to want to chair flip to turn this axial into equatorial. And so now it's pointing off to the side, and so now it's not interacting really with anything. And so what's going to happen is it's going to spend most of its time in this form, okay? And so you can look at it this. People have actually calculated this. And so if you just have hydrogens, it's going to spend, this group here is to spend its time as a axial or equatorial. And if it's a hydrogen, it doesn't matter because they're equivalent. How about that? So because it's just a hydrogen. But as you start making these larger, right, it's going to spend more and more of its time in the equatorial position. Okay, so methyl spends methyl, ethyl, isopropyl, it's spending 97 to 95% of its time in this conformation. If you put a giant T-butyl group in here, it's essentially locked into here. Remember that it's basically never going to spend any of its time with that T-butyl group in the axial position. Okay, and so what you can do is you can then and so if you wanted to lock it into this configuration, you just put a T-butyl group on here. Okay, but large groups want to be equatorial. Okay. Now the problem is, what if you have more than one thing on it? But that's non-hydrogen on there. Okay, and so we can't have that. Okay, and we can designate that as a cis and trans. Okay, and so if you have so when we do this designation, if both groups are up, so in this case, right, so up, right, or down, doesn't matter. We call that cis, okay, the cis isomer. If we have one up and one down, then that's a trans. Now, if we have a wedge, like here, we assume that that's up. if we have a dash, that's down. Okay? And so like here you've got two wedges, that means they're both up, so that means this is cis. Here we have a wedge and a dash, so we have an up and a down. And so it's trans. Okay. Now, cis and trans does not equal axial and equatorial. You can have cis things where they're both axial. You can have cis things where they're both axial, and then cis where they're both equatorial. And you can have one where one's equatorial and one's axial. So don't get that confused. Cis and trans only is determined by up and down. Okay. So here, right? So here we've got the cis. We've got cis 1,3 dimethylcyclohexane, and so if you do the chair configuration, right? So for here, right, the carbon-carbon bonds pointed down, so that means the axial is pointed straight down. So that must mean the hydrogen that's not shown is the down. So that makes this the up. Same thing goes with here. The carbon-carbon bonds are pointed down. So that means the axial is down. This one's pointing off to the side, so it is in fact. So this is also the up. When we do the chair flip, they still remain up. Okay, up, up. But now they're both axial, and so now you've got this massive interaction here, where they are, where they're going to be interacting, and so it's going to spend almost all of its time, basically all of its time in this configuration. If it doesn't help, okay, so for in this case, so you've got here, this is equatorial, right, because the bonds are pointed down, okay, so that's there. Here, the carbon-carbon bonds are pointed down, so this is in fact the axial. That's a little hard to see. So the hydrogen is equatorial. When we do the chair flip, now this one becomes axial and this one becomes equatorial. So we have one axial, one equatorial. No matter which form we do, we have one axial and one equatorial. So it doesn't really matter in this case. So it's going to spend half its time in one, half its time in the other, because it doesn't matter. They are energetically equivalent to each other, okay, because you've got one axial, one equatorial. Here they are not. This is much, 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 much more stable than this form right there. So this is going to be the preferred conformation. So when I say that they're identical, I just mean energetically identical. Okay. Now, if you have two things that are so if you have to make a choice, now instead of just having like two methyl groups, you've got two groups that are of different sizes. Now you've got to take into account the size. Sorry about that. The size of the molecule, or size of the group that's hanging off. So here you've got this giant T-butyl group, and then you've got a methyl group. Now, methyl group's not trivial, but compared to the T-butyl group, it's much, much smaller. So this one is basically a methyl group with hydrogens hanging off of it. Here, this is a methyl group with methyls hanging off of it. So if you can kind of think of it like that. And so this one is the up because it's on a wedge. This one is the down because it's on a dash. Okay. So if we draw this out, right? So for here, right, this is the up, that's the down. So the carbon-carbon bonds are pointed up. So this is going to be the axial, right? And so here the carbon-carbon bonds are pointed up again. So this is the axial, so that means this is equatorial. So when we chair flip, right, this becomes equatorial, right? Because there's a hydrogen pointed straight down. And in here, the carbon-carbon bonds are pointed down, so that means this one is axial. Okay. And so the question becomes, which one of these is more stable? Well, what we want to do is we want to put the larger group equatorial. So if we want to try to minimize the interactions, okay, and so it's still going to pay a penalty, right? Because it's still going to have the methyl group axial, but it's not going to be nearly as big of a penalty if we were in this form where you had that T-butyl group in the equatorial position. So this is the one that it's going to want to be in, and so you want to try to get as many of those large groups as as equatorial as possible. You may not be able to get them all, depending on the configuration, but you try to do the best you can. So for bicyclic alkanes, we talked about this, I think, in chapter 2. So you can have these things fused. So you can, in fact, have a cis and trans form. Okay, and so this is, notice how, this hydrogen is above these carbons, so this is up. And then this one here, this one is down because it's below all these carbons. Here, this hydrogen is above the carbons, and so this one's up. So this one, and so this one is going to be above, sort of if you look at the, if you look at it from the side here, right, this is up compared to the other carbons, so like that, and so this one is also up. So that's why these are both up. So that's why it's cis. This one is trans, right? Because you got an up and a down, and it's designated as two wedges as opposed to a wedge and a dash, so like that. And so this cis again, like with the double bond, right? It makes the molecule kink, so like that, while the trans makes it flat. Okay, and you can also have all sorts of crazy ones where you fuse these things together. Okay, good luck.